Hi, in this video we will learn an alternative approach through which one can check if given vectors are linearly independent or not. Well, this approach is based on an easy fact which I encourage you to sit and think about it and make sure that you have all pieces in mind, that says every sequence of elementary row operations generate matrices or matrix whose rows are non-trivial linear combinations of the rows of the original matrix. So if you do elementary row operations after any number of steps, the matrix you get, all the rows are linear combinations of the original rows of the original matrix, and it's not just linear combination but non-trivial linear combination. For example, just the elementary row operation themselves, not a sequence of that, it's very clear that they will generate linear combinations of the rows of the original matrix, but you have to do a little bit work, but it's not difficult. You can see it obviously. Let's do this through an example. I have this matrix here. What is this matrix? 1 2 negative 1, 0 1 negative 1, and 2 0 2. I start reducing this matrix. The reduction goes like, okay, I want to make this guy 0. So this means that I have to multiply negative 2 to row 1 and add it to row 3. This will give me 0. This will give me what? Negative 4. And this will give me just 4 itself. And the other rows, we don't change them. Yes, the operation doesn't pose any changes, modifications there. Okay, and then we do, well, we want to make this guy 0, so it means that we multiply row 2 by 4 and add it to row 3. So this gives me what? This gives me 0, then 0 and 0, and here will be 0 1 negative 1 1 2 negative 1. Okay, if you look at this operation, if I start marking the rows of the original matrix, row 1, row 2, row 3, the matrix, the rows of the first matrix, after applying the row operation, I will denote them by R1 prime, R2 prime, and R3 prime. And for the third one, well, I will do double prime, R2 double prime, R3 double prime. Okay, then what I have here is that saying that, okay, so R3 prime, the third row of the second matrix, is given by these guys. And well, R1 we didn't touch it, R2 we didn't touch it. Yeah. And then in the second step, we did use R3 prime and R2 prime and did generate R3 double prime. And while here R1 double prime, we didn't touch R1, so it will be R1 prime, which is the same thing as R1, so it will stay the same as the original row 1. R2 double prime is R2 prime, which is again R2, and you can see that we didn't change that one. Oh, we didn't change, I copied wrong, but this is negative, okay. And R3 double prime, now we see that is equal to 0. Yeah. What else we know? We know that, okay, if I plug in these things, R3 double prime is R3 prime plus 4R2 prime. And this guy is R3 prime. I know that it is R3 from here minus 2R1. And we know that R2 is same thing as R2 prime is same thing as R2. So we have this. And what we showed here is that negative 2R1 plus 4R2 plus R3 is equal to 0 vector. Well, what can you conclude from this thing? So this means that row 1, row 2, take them as vector, row 3 are linearly dependent. And well, this can be well organized in a theorem thing, and let me just show you what are these steps on this thing. So first thing is that we can see that if row echelon form of a matrix A has 0 row. What does this mean? This means that a linear, a non-trivial linear combination of the rows of the original matrix A is equal to 0, is 0 vector. That's just, I'm writing it using the fact I wrote for you up there. Then, well, if a non-trivial linear combination of some vectors is 0, that means that those vectors are linearly dependent. So let me just write the rows of A are linearly dependent. So row echelon form of a matrix, it has a 0 row, means that they are linearly dependent. The rows of the matrix are linearly dependent. On the other hand, we know that non-zero, counting the non-zero rows of row echelon form gives us a number. We called it rank of A. So this means that rank of A is less than number of rows of A. Let me just open a little bit space here for me. Row of A, number of rows of A. Very nice. Now we see that if number of rows of A is bigger than, strictly bigger than rank of A, then rows of A are linearly dependent. On the other hand, if you have rows of A are linearly dependent, means what? Means that you have C1 R1 plus C2 R2. These are vectors, the rows, not the columns, rows, and CM RM are equal to 0 for non-zero C's. Okay. Then we can assume that one of these guys are non-zero, and actually we can assume that it is 0. So let me just assume, without again loss of generality, we can assume that C1 is 1. And that means what? That means that we can write row 1 as minus no, sorry, not right. So we have row 1 plus C2 R2. I'm assuming just C1 is 1. If it is not, you divide that whole expression by C1, assuming that C1 is non-zero. Okay, now that this happens, then I can apply these row operation. What row operation? So I can replace row 1 by row 1 plus C2R2, and row 1 then another time by C3R3, and then continue these operations. So these are row operations I'm claiming we do. If you do this operation, the row 1 will become this guy here, which we already know is equal to 0. So that means that the, this way. That means that row 1, so let me write, row 1 becomes 0 row after applying these elementary row operation. And that means that row echelon form of this matrix has a 0 row. And you see that this is a two-sided fact. So in other words, what I sketch up there is a proof for this theorem that let V1 up to Vm be rows of matrix A. Then V1 up to Vm are linearly dependent if and only if, this is why we have going and coming back. You see, once we went this way and once we came back this way. If and only if rank of A is less than number of rows of A. And that's something that gives us a little bit different approach. Why? Well, if you're trying to check if some vectors are linearly dependent, put them in the rows of a matrix, and then row reduce and find its rank. If the rank is less than the number of these vectors or number of the rows of that matrix, those vectors are linearly dependent. Okay, let's see some examples for this. Determine if the given vectors are linearly independent or not. Well, first thing is that you have to put them in the rows of a matrix. Yes, so we put them in the rows 3, 0, 1, 0. So this goes for the first row. 0, 2, 0, 1. This goes for the second row. And then 0, 0, 5, negative 1. This goes for the third one. This is the matrix A. And, well, it happens in this case that this guy is row echelon form. You see, this guy is row echelon form. And right away you can say that rank of A is equal to 3, which is equal to number of rows of A. It means that the rank of A is not less than rank of number of rows. That, based on that theorem, then we know that the vectors, the rows of A are linearly independent because the number of rows are not strictly bigger than the rank of A. Okay. Well, how about this other one? So we put them in the rows 1, 2, negative 1, 3, 4, 0. Well, it's not row echelon form, so we have to do some works to make it row echelon form. So here we do row 2 plus row 1 and row 3 minus 4 row 1. And what we get is 1, 2, 0. So we are adding 5. And this guy here, negative 4 times that is 0. And then negative 4 plus negative 4 times 2 is negative 8, and then added to that is negative 8. Then let's just do row 2 divided by 5. This way we get 1, 2, 0, 1, 0, negative 8. And then multiply row 2 by 8 and add it to row 3. We get, not 0. This doesn't change. This will be 0, 0, 0, 1, and 1, 2. This is now row echelon form, and right away we say that, okay, if we started with this guy, the rank of the matrix is equal to number of non-zero rows, which is equal to 2. And it is obviously less than 3, which is number of rows of A. And by the theorem, we can see that the vectors, the given vectors, are linearly dependent. And well, this actually is, in general, it is true that you see the number of the vectors, if you have more vectors than their components, then the rank of the matrix is always less than both rank of number of rows, less than equal to number of rows, and also rank of A is less than equal to number of columns of A. And this is always and. Why? Because every column can have at most one leading entry. So that means that the rank cannot be bigger than number of columns. So if the number of columns here means that number of entries, number of components is less than number of the vectors, then always this will happen. So rank of A is going to be always less than rank of number of rows of A. Let me write this as a corollary, or what your book writes it as a theorem, which says that any set of m vectors in Rn, so we have n components, but m vectors is linearly dependent if the number of the components are less than number of the vectors. Well, it means that doesn't matter, you don't need to think about anything. If you have 4 vectors, I'm just writing random vectors, any 4 vectors in R3 are linearly dependent. Or any 5 vectors in R2 are linearly dependent. So the maximum number of linearly independent matrix vectors in Rn is n vector. It cannot be bigger than n. So let me write this as a corollary. The maximum number of vectors in Rn that can be linearly independent is n. So any number of vectors bigger than n are going to be linearly dependent. Okay, so this gave us one new approach to check. One thing that you have to do is turn them in the rows, because this approach talks about the rows of matrices, and you see that this provides something for us to show very nice proof of a very good theorem.